The talk is Zeno goes to Copenhagen, a dilemma for measurement collapse views of quantum mechanics. So Copenhagen here obviously is the Copenhagen interpretation, or one of the many, many things that is meant by the Copenhagen interpretation. Here we're using Copenhagen interpretation to mean a view of quantum mechanics where wave functions really collapse, and they collapse on measurement. Now, of course, the word Copenhagen interpretation is used for many mutually inconsistent things, but this is one of the things it's sometimes used for. That's the one we're focusing on. Part of our motivation for being interested in this topic, and the reason why it's in this session, is that one version of the Copenhagen interpretation, so understood, is a view where consciousness collapses the wave functions. Only one version. Maybe you can understand measurement independently of consciousness, but it's part of our motivation to think about it, not least because it offers the exciting prospect of a role for fundamental consciousness in the physical world. I take it Foundational Questions is all about exploring crazy ideas and seeing if we can make sense of them. That's very much what we're doing here. We're certainly not endorsing the idea, not sure that we believe it, probably not, but we think it's interesting to see if you can take that old idea and make it rigorous and make it work. So that's something we've been trying to do for a little while. We've actually come across some problems, and one of the problems is what we want to talk about today, that measurement collapse interpretations suffer from a dilemma that arises from the quantum Zeno effect. We got there through thinking about our own particular approach to consciousness and collapse. Then we thought, okay, this problem actually has a quite general class of application that we think may not have been noticed to date. So we want to raise the problem here and raise the question of whether it can be solved. We think at the very least it puts very strong constraints on the form of a consciousness collapse or a measurement collapse version of quantum mechanics. So really basic quantum mechanics. There's the Schrödinger equation with a wave function that usually evolves linearly, typically in states of superposition. There's a measurement postulate that says when you measure an observable, it takes on a definite value, and the wave function actually transitions into a more determinate state. Very familiar formalism, at the very least. Measurement collapse interpretations, as we will understand them, are interpretations that take this standard dynamics at face value. The objective state of the world corresponds to a wave function. It's really out there. The wave function really evolves according to the Schrödinger equation and really collapses on measurements. This is a kind of objective collapse interpretation where the trigger for collapse is measurement. And I take it this is at least a very familiar way of thinking about quantum mechanics. Here's a picture we found on the internet of this view where you actually get to see some people calling this the Copenhagen interpretation. Now, of course, as I said, there's a million different Copenhagen interpretations of quantum mechanics. Arguably, the term ought to be reserved for the views of Bohr and Heisenberg, which this certainly was not. Still, the word gets used for Bohr's view involving complementarity, sometimes gets reserved for anti-realist views in the shut up and calculate spirit. We're using it here for the measurement collapse view. Somebody pointed out this view is really promulgated by von Neumann and Wigner, who are both Hungarian. So we should actually have called the talk Zeno Goes to Budapest. We'll consider retitling it that from now on. Anyway, but we couldn't resist Zeno Goes to Copenhagen, which is why we're using the word this way. Now, there's a million other interpretations of quantum mechanics. We're not arguing against them. We're not rejecting them. Everything from many worlds to quantum Bayesianism. We actually like quite a lot of these. Our project here is to merely explore, to see if, I think it's fair to say that although measurement collapse views are in some sense a very familiar way of thinking about quantum mechanics, people working in quantum foundations don't take the idea particularly seriously. It's usually rejected out of court. We're interested in whether this kind of view can at least be explored and developed, where it's at least comparable and it's as respectable as, say, spontaneous collapse theories like GRWs and pearls, and that's our project here. Now, there's a very standard problem for measurement collapse theories, perhaps the original measurement problem in quantum mechanics, which is what is measurement. The ordinary notion of measurement is imprecise and anthropomorphic. It's awfully hard to see how it can play a role in fundamental physics. One of the things which has moved people away from these views, and of course it generates all the familiar Schrodinger's cat puzzles. Where in this big process does measurement actually occur? It looks like the framework doesn't say. But we think where some people see a problem, we see a cool challenge and an opportunity. Can one actually, where you have an imprecise term, well, that's a challenge. Make that term precise. So question, can one make a measurement collapse view precise? And our view is that, well, it's in principle, one ought to be able to with a couple of things. First, a precise criterion for where measurement takes place, rather than just this imprecise notion. And second, a precise dynamics of measurement-triggered collapse. So can we get a precise notion of measurement and a precise dynamics for collapse? If one can, then there's all kinds of interesting promises here in the background, not least the fact that it looks like various different versions of measurement collapse quantum mechanics with different ways of making these notions precise will all be subtly, empirically distinguishable with interferometer experiments and the like, which actually offer a potential empirical program of empirically testing all of these views, much as people have done with spontaneous collapse views. I think neither Kelvin or I is going to stick our neck out and say that we're predicting that any of these, that you're going to find that these views are true, but nonetheless it's nice to have a potential empirical program. Okay, how do you take make measurement collapse precise? Well, there's one very old idea here, associated most closely with Wigner, that consciousness provides the criterion for measurement. And this has a number of advantages. First is the idea that consciousness is actually a precise property. Now, this is philosophically and scientifically controversial, but many people accept that consciousness is either present or it's not. Where it's present, it comes in degrees, but nonetheless, it's a binary property. A number of philosophers have argued for this. If that's true, then, okay, you've satisfied one of the desiderata for a theory. We have a precise trigger for measurement. Of course, that still raises the question of what the physical criteria for consciousness are, but increasingly precise theories of consciousness and its connection and the physical criteria for consciousness are beginning to be developed. Integrated information theory is one that's being talked about here today. Whatever you think of it as, it's at least relatively mathematically precise. So we're going to basically look at the prospects for combining theories like IIT or other mathematically precise theories of consciousness with the consciousness collapse view. And of course, though, in the background, it's got the big philosophical prospect of offering a causal role for consciousness in the physical world. If, like me, you're inclined to think there are arguments that consciousness is irreducible to something physical, the next question that always arises is, now, what on earth role does it play in the physical world? There's a well-known philosophical view here called interactionist dualism, most closely associated with René Descartes years ago. I think consciousness is a fundamental property distinct from all physical properties. Physical processes affect consciousness, and vice versa. The problem for this view instantly is the famous interaction problem. How can this work? And in particular, how can this be consistent with the apparent closure of physics? You get a situation that looks something like this. Some physical processes affect something in the brain, affect consciousness. Consciousness has to re-affect the brain, which then affects action. And the standard objection is this violates the causal closure of physics. It violates everything we know about physics. But on the other hand, in the spirit of, I'm committed to the idea that to solve the problem of consciousness, we're going to need a crazy idea or two. In the last talks, we saw some cool, crazy ideas, idealism, illusionism, and so on. I think they're all worth thinking about. But in this, the spirit here is to look at consciousness collapse interpretations in part to see if we can make sense of the crazy idea that consciousness here plays a role in the physical world. So it looks like if you want to look at anything like standard physics and find a potential role for consciousness in the physical world, this is the place to look. But the challenge, I take it, is what is the dynamics? What is the precise dynamics of a consciousness collapse view or of a measurement collapse view more generally? So Kelvin and I have been working on this now for a few years, and we've got a relatively positive paper called Consciousness and the Collapse of the Wave Function, where we're exploring rather than endorsing the view, but trying to see if we can make sense of it. But we came up against this problem with the Zeno effect. The central idea that we wanted to exploit in making sense of the dynamics of a measurement collapse view or a consciousness collapse view is that there are certain special properties that never enter superpositions, and that thereby collapse everything they interact with. And we call these M properties. So M properties are properties which, as a matter of fundamental law, can never enter quantum superpositions. Why M? Well, you can think of them as like, measurement device properties, like the pointer never enters a superposition. You can think of them as Medusa properties. Everything they look at everything that looks at them turns to stone. Or you can think of them as mental properties. Consciousness, which is the direction you eventually want to go. And this, I think if you actually look at Wigner carefully, it seems that Wigner might have been endorsing a view a little bit like this with consciousness. He said consciousness is special because it can never enter superposition. He said if someone had superposed consciousness, they would be in a state of suspended animation. The idea we're running with is there are certain special properties that never enter superpositions. Maybe, for example, something in the superposed entity in the world affects your brain. The neural correlates of consciousness would enter superposition. That can't happen. Collapses onto a definite state, collapses everything entangled with the state. Then there's so if you want to combine this idea with consciousness collapse, you'll get a basic principle that says consciousness can never enter superposition. Or maybe if you want to do this in more straightforwardly physical terms, the neural correlate or the physical correlate of consciousness, or an IIT property. Okay, it's a very simple idea. There are certain special properties, the M properties, the measurement properties, that never enter superposition. Just for the purposes of illustration here, you can think about combining it with integrated information theory. This would work just as well for any precise theory of consciousness. We say, there's a PCC observable. PCC is the physical correlate of consciousness. On this view, there's going to be some kind of quantum observable that constitutes the physical correlate of consciousness. Different values of that observable will correspond to different states of consciousness, and these resist superposition. So in IIT, there's something called Q-shape, short for qualia shape. Everyone knows phi from IIT, but there's this other thing which is arguably more fundamental called Q-shape. Different values of Q-shape are meant to correspond to different states of consciousness. Think of all these as different eigenstates of the Q-shape observable. And then, the idea would be this IIT property resists superposition. The brain has always got to be in a definite state of that observable, and that thereby collapses everything it comes into contact with. Now, wonderful, simple framework. Unfortunately, it's got an equally simple problem. If you take the absolute version of this, where M properties can never superpose, then it just follows from the quantum Zeno effect that they can actually never change via Schrödinger evolution. It's just a mathematical fact that via Schrödinger evolution, quantum observables never have to be able to enter superpositions to change. If you've got something that doesn't enter superpositions, it can't change. So if consciousness or its physical correlate was an absolute M property, it could never change, which is a rather serious problem. How does consciousness get going in the early universe? No consciousness might begin to wink in on one branch of the wave function. Bing, collapses back to no consciousness with probability 1. Worse, if you're napping right now and unconscious and you want to regain consciousness, sorry, it's not going to happen. Too bad about that. Okay, rather serious fatal flaw for the view. Initially, we thought this was just going to be a problem for a particular approach to consciousness collapse, the M property view we were thinking about, but now it starts to look like this Zeno effect raises analogous problems for measurement collapse views quite generally. These problems have a limited range of solutions, I think, that heavily constrain any Copenhagen-style view. So let's make the notion of measurement precise just by saying there's some precise relation MSO that says observable O is measured in a system S, and perhaps it's measured by some other system, S prime, but we'll just represent this as O is measured in S. The measurement collapse view then says the wave function of S collapses onto an eigenstate of O if and only if MSO obtains. So first question, is measurement itself a quantum observable? Is the fact that measurement takes place an observable in quantum mechanics, which is basically to say it's a quasi-classical property, a property of a classical basis state that corresponds to a Hermitian operator? Prima facie it is. It looks like you can perform observations to determine whether one system is measuring another. Standard ways to think about measurement would be an observable. But then to raise the Zeno dilemma now, we can ask the question, can measurement enter superpositions? Can it be the case that a system is in a superposition of measuring another system, measuring a certain observable, and not measuring that observable? So can the world be in a superposition of this, O is being measured in S, and O is not being measured in S? Either way, you get serious problems. If measurement can enter superpositions, it just looks like the dynamics is ill-defined. If a system is in a superposition of an observable being measured and not being measured, does the wave function collapse? This framework is just not going to say. On the other hand, if measurement is an observable that cannot enter superpositions, then measurements can never start or finish. And that's just the quantum Zeno effect, because we know that measurements that can't enter superpositions can't change. I mean, the quantum Zeno effect is often put informally by saying if one measures an observable too often, it's slow to change. If you measure it continuously, it can't change. If you continuously measure an electron's position, it'll be frozen in place. So it's like the watch pot never boils effect. But here we're applying the QZE to measurement itself and saying, can measurement itself enter a superposition? If not, it's as if measurement itself was constantly being measured and thereby could never change. If measurement can't superpose, it's as if it's being continuously measured. It can never start or finish. The math of QZE is just that for an observable to evolve from one definite state to another, it must pass through superpositions. If it can't change in value. Okay, so then it looks like then if measurement is an observable, you got serious problems. You get, if you like, an inconsistent set of claims. You can't have all of the following. Measurement's an observable, measurement's non-superposable, measurement is changeable, measurements can start or finish, and if an observable is non-superposable, it's not changeable. So you've got to reject one of these claims. I mean, you can look at rejecting 2, 3, and 4 in various ways, but we think obviously the best thing to try is to reject one and say, okay, measurement is not, in fact, a quantum observable. But that really narrows down the range of options that are left open. I think there are basically 3 options. Measurement is a classical property, measurement is a non-physical property, perhaps associated with consciousness, and measurement is a wave function property. You might want to measurement as a classical property. Maybe you've got the idea the world contains both quantum and classical processes. Measurement is a classical process, and so not subject to quantum laws like QZE. Maybe you can find something like this in Heisenberg and Bohr. Not enough time to go through this properly, but I'm inclined to think that you just can't make this work. There's no quantum classical distinction at the fundamental level of reality. If you want to think of classical processes as arising from quantum processes by decoherence or collapse and so on, maybe you get some exceptions here, but if you work through it, it just can't avoid the Zeno effect for the trigger of collapse. So we don't think this option is promising. More promising, you might say, okay, measurement is a non-physical property, strong dualism. You have a physical realm, you have a mental realm. Why should the mental properties be subject to principles like Schrödinger evolution in the first place? And Wigner himself was a strong dualist. Henry Sapp has investigated this view. Unfortunately, it's not quite so simple. It looks like the QZE problem extends to any version of dualism on which there's a physical correlate of consciousness. Most dualists these days, there are many, I'm sometimes a dualist myself, nevertheless believe in strong correlations between physical states and consciousness. If it turns out, if there's a physical observable P with distinct eigenstates corresponding to distinct states of consciousness with a systematic correlation, then QZE problem just arises all over again for that physical correlate of consciousness. If it can enter superpositions, then consciousness can enter superpositions. Measurement dynamics is ill-defined. If it can't enter superpositions, it can never change. So that's going to be a problem. I think the alternative, if you really want a way out here through dualism, you need a very strong form of dualism, where consciousness doesn't have a precise physical correlate, where it can vary independently of underlying physical states. That's a view which is too strong, I think, for most dualists these days. It's too strong for me. Arguably, Henry Stepp's view has this form. But anyway, that constrains one of the options quite seriously. But, there are some problems. It's very radical. You need a new non-physical dynamics of consciousness. And it turns out that actually once you start working through the dynamics, it gets very messy. So the view we're actually inclined to go for here, as possibly the best option, is to say, okay, measurement is not an observable. It's what we might call a wave function property, a property of a wave function as a whole. It's not the kind of quasi-classical property that enters superposition. Take properties like the spread of a position wave function, or having such and such a kind of superposition, or the degree of decoherence in a wave function. These are all wave function properties. They're not observables that enter superpositions. And it seems to be left open that measurement might be represented as that kind of property. So, the spread of a wave function. Now, of course, treating measurement as a wave function property is, I think, a fairly revisionary extension of standard quantum mechanics. It's certainly not built in to the standard view, but we think it may be the best remaining option for avoiding these Zeno problems. And so in the limited time left, I just want to say something about what we see as a view worth thinking about. I mean, even earlier on when I talked about the M property frameworks, properties that resist superposition, maybe it occurred to you, okay, well maybe let's not make that an absolute claim. They're never superposed. Maybe they merely probabilistically resist superposition. So the approximate M property view says, as M properties become more superposed, collapse becomes more probable. Here there's an analogy with the Penrose view of space-time that some of you will know, that collapse is triggered when space-time structure becomes too superposed, too much superposition. You get a trigger for a collapse. Penrose's view is not a measurement collapse view, but it avoids the Zeno problem in this way. So our thought is maybe take a framework like that and extend it to these M properties, such as correlates of consciousness, via some kind of stochastic collapse of the PCC operator. So say we've got a PCC observable like Q-shape that's a correlate of consciousness. We say small superpositions of the PCC yield small superpositions of consciousness, and then its consciousness resists superposition. It can only enter very small superpositions. As they get larger, they tend to stochastically collapse. So superpositions of Q-shape will collapse. Let's say, for example, superpositions of Q-shape collapse proportionally to wave function spread or to degree of decoherence or something like that. We don't have time to go into the math here, but we think this idea can be made rigorous by combining IIT with Pearl's continuous spontaneous localization theory, which will be familiar to a bunch of you as a kind of a continuous version of a probabilistic objective collapse view. On Pearl's view, position stochastically localizes over time, and he's got some equations for it. So you can think about, for example, now taking that Pearl-style view and combining it with IIT, which gives you this observable Q-shape and a distance metric on it, and make the claim that Q-shape stochastically localizes in much the same way that position does on Pearl's view. You get collapse towards definite Q-shape with the Born probabilities. So, I mean, this is really kind of a weird mashup of Tononi, Wigner, Pearl, and Penrose on this view. But just to get the rough shape of the view that would arise from this, you've got a basic correlation principle in the background that says Q-shape or whatever is a physical correlate of consciousness. Any psychophysical theory could be substituted there. Combine that with the idea that consciousness stochastically resists superpositions. Superpositions of consciousness have a very strong force to collapse. Get through combining Wigner, Pearl, and Penrose, and you get this dynamics. So when someone observes a superposed particle, their PCC will become increasingly superposed. Consciousness will stochastically collapse to a definite state, collapsing PCC, collapsing entangled physical processes, and that will actually cause actions, like there's a particle in position A. So we have a causal role for consciousness on this view. Now, there's 1,000 issues for this view, and you'll have thought about a bunch of them already. How can consciousness be superposed? Does it play the right kind of causal role? How do we set parameters for this to be empirically plausible? How to make it relativistic? And can we get empirical evidence? In fact, you might even think, one cool thing about this view is that, again, it's empirically testable. Arguably, the simplest version of this view is not just empirically testable, but empirically tested and refuted. One that says, for example, that superpositions of phi equals 0 and phi equals 1 collapse. Arguably, that's testable with existing quantum computers. Okay, so my time is up. To summarize all of this, consciousness collapse views need either, through this analysis, no physical correlate of consciousness, very strong claim, strong dualism, or a wave function physical correlate of consciousness, as in this theory, and measurement collapse views more generally need much the same thing, strong dualism or measurement as a wave function property. We think those are very interesting and surprising constraints on these views. So our conclusion is, it's not easy to be a measurement collapse or a consciousness collapse theorist. Speaking for myself, it's made me more skeptical about these views working through this, but nonetheless, I think it's informative. At the very least, there's a research program of developing, refining, and testing these measurement collapse interpretations, and perhaps there's at least some small hope remaining for a causal role for non-physical consciousness in physical reality. Thank you.